check it out. You can rewatch that and see it. But or if you have further questions, ask them on the comments there. Okay, cool. So yesterday, back in lecture, we finished off by talking defining this new vocab word, orthogonal, right? And this has to do with two vectors, and it's basically a new synonym for the word perpendicular, right? So perpendicular has to do with geometrically like lines or something like that. But when we're talking about vectors, we like to use the word orthogonal, but it just means that they form a 90-degree angle. Okay. And we discussed a little bit of what it means here, using that formula about angles, right? We talked about angles in general and how that relates to the dot product of the two vectors. And basically, if you can compute the dot product of two vectors, then you can basically compute the angle that they form. And that's what we have. That's what we see here. So the next thing we're going to talk about, the last thing for this section basically is the orthogonal projection. And the orthogonal projection is geometrically, I have this picture here. You're projecting U onto V. You might be, if you look at the formula in the book, they might use different names for the vectors. But in the picture here, what's happening is you're basically taking this vector, you're treating this vector V as if it was the ground, and this U is like something sticking up at a certain angle. And what we're looking at is we're imagining that there's shadow casting or light casting straight down. And so you were looking at the shadow of U on V. That's kind of how I like to think of it. And so what we do is we get like a line, like an imaginary line that goes like straight down and forms a 90-degree angle with V. This is the orthogonal part of orthogonal projection. That's why it's called orthogonal projection, because we get a nice right angle here. And P is this vector that comes right here. Let me use a thicker point. It comes out like that. So this here is P. Okay, and so it's projecting this down. So, imagine a projector like projects light onto a big board. Imagine there's a projector out here, and this V is your wall, and this U is something that's like obstructing it. And so there's a projector out here that's pointing straight this way. And so the P is like the shadow of U on V here. Okay, that's kind of the idea here. So this is geometrically, conceptually what's going on, but let's talk about how we'd actually use a formula to figure out what P actually is numerically. The formula is not super, it can be a little harder to visualize. That's why I started with the picture. But basically what you're going to do is you're going to take the dot product of the two vectors, V dot U, okay, divide by the norm squared of the vector you're projecting onto, and then multiply that. Now, this is going to be, right, so this is a dot product of two vectors. So this is just a number now, and then you divide by a number. So this whole thing that we're seeing here is just a number, but we want a vector. So then we take this and multiply it by V. This dot here, I shouldn't maybe use a dot. This is just like scalar multiplication here, because this is just going to be a number. We scale it by V. Basically, we know it's going to be along V here, right? Because V is this vector. V is this vector that we're projecting onto. And so we know that P is going to have to go along V somehow. And so we're just going to want to scale it down or up, right? Again, based on the picture here, I clearly have to scale it down, but you can see that if I made U way longer, then I would have to scale it up to make P long enough, right? But the point is that we're going to need some scaled version of P. So you can think this here is just telling us the scalar multiple. This first part here is telling us the scalar multiple here, because this is clearly just a scaled version of V. And this tells us exactly how much that scalar multiple needs to be. Okay. You could maybe combine like this formula up here along with some knowledge of trig, and like prove this in like in a pinch, right? Like if you're like, oh, that looks like a scary formula and I don't know how to memorize that, it would be, you know, a cool exercise to prove this using some trig here, right? There's a right triangle here. So I'm sure you could figure out how this angle and then this length and this length are related to each other, right? Cool. Okay, cool. Any questions on orthogonal projection? So this is just a nice formula, and on the homework, it's there's going to be some relatively straightforward problems of like project this vector onto this vector, and you'll just use this formula and just make. And I think one of the tricks here is making sure you have your u's and your v's in the right order, making sure u is in this formula, u is the one that's projecting, and v is the one that's being projected onto. And so it is important. This formula would be different if you switched u and v. You'd get a different vector. Cool. Any questions on this? Okay, cool. So the last slide I have here is just a couple of theorems from the textbook. I don't want to spend too much time on this because I want to move on to the next section, but they have some fancy names, and I don't think these are as important in this class as some of the other stuff we've talked about. So I'll just kind of go through them really quickly. I don't think there's even any homework problems about it, about these theorems. So I won't dwell on them too much, but it's nice to have them in your notes somewhere in case. I do think that your notes shouldn't just be for this quarter. It should be like a resource that you keep, you know, for basically for the future. And so it's nice to have, it would be nice to have these formulas somewhere, even if you don't end up using them this quarter. It'd be nice to have them at some point. So basically you get two vectors anywhere, and you can take their dot product, and their dot product would just be a number. So this is the absolute value in the sense of just like a number. And this is going to be less than or equal to the norms of these two numbers. And you can actually justify this using that formula about cosine of theta, right? If you wanted to figure that out, you can use this here, use this formula, use that formula to prove this inequality here. Again, that's not the most important, you know, it's not the most important thing we do here. So cool. So let's then move on to the triangle inequality. The triangle inequality has a nice picture to it. Basically, when you add two vectors together, right, you get a little triangle picture, right? Because you get, like, if this is v and this is u, then you get a triangle here with u plus v, right? And what the triangle inequality says is that if you just look at the length of u plus v, right, this is always going to be less than or equal to the length of u plus the length of v. Now this one you might not always use, you might not use like directly in this class, but it's something like, it's a good intuition to have, right? Basically the norm of the sum of the two vectors is less than the sum of the norms. Yeah, so that's a good way to say it. The norm of the sums, or maybe I should say length. The length of the sum is less than the sum of the lengths. Okay. Let me write that. Length, the length of the sum is less than the sum of the lengths. I say less than or equal to is fair. And when you draw the picture, it becomes quite clear that this is going to be true, right? if imagine you're driving somewhere, driving straight somewhere is going to be quicker than driving somewhere else, making a stop, or driving somewhere else and then from there driving to your ultimate destination, right? Because you make this triangle. And so that's kind of how you should picture this triangle inequality here. Okay, cool. Again, just a couple of theorems that would be good to have in your notes for reference. Triangle inequality might come up in some way or another, usually in like the justification part of things, less in the computational part of things. But it'll be good to have in your notes again as a reference. Okay. Cool. How am I doing on time? Okay. And this is just the last little bit of section 1.2. I was planning on finishing all this yesterday, but I didn't quite get to it. So again, orthogonal projection, this nice formula. It comes up on the homework, so make sure you're pulling those up, pulling up that homework and practicing some problems. These theorems don't really come up in the homework, but they'll be good for reference, either later in the quarter or if nothing else, it's just good to have in your notes. Okay, cool. Any questions before I move on? Okay. I'm gonna go ahead and save this and then open up the next section so we can get started on that. Hopefully get through most of this, but we probably won't finish today. Okay, so now we're gonna get to the real, where we wanna spend most of our time today, which is section 1.3, which is about matrices, determinants, and cross products. So this point, maybe many of you have probably heard of matrices. I was looking at the discussion board where we're kind of sharing, a little bit about ourselves, and some people have said that they've somewhat recently taken a Math 31 class. In a class like that, then you're definitely getting to know how matrices work and determinants and all of that. So you're probably, if you've taken that class, then you're probably pretty good at this. Or if you kind of struggle with this, then that maybe is a good class to take after this, or maybe after 10B if you want to take that right away. But yeah, taking that sort of linear algebra is what that class is called. Would definitely help with, that's definitely where you're going to get a deeper understanding of this stuff. Today we're just going to kind of breeze through a bunch of matrices and determinants, and then we'll touch on it again a little bit on next Monday and dig into a little more detail. But yeah, so we're just going to kind of breeze through it today. So just enough of an understanding so that we can use matrices in some of our computations when we start doing actual calculus. So yeah, notice that we haven't really done any calculus. A lot of it has been algebraic and geometric so far. And it's basically, before we were able to do single variable calculus, we have to know all this pre-calculus in regards to single variable stuff. And now we're getting into multivariable calculus. So we need to make sure we have the basic algebra and geometry down first. And it's a little more complicated in multiple variables because we have to deal with, as you'll see, matrices and vectors and stuff. So, okay, so let's talk about matrices. So if you remember, a matrix is just like a grid of numbers, right? So it's an array of real numbers and arranged in a grid, right? For this section and for most of this class, we're just going to deal with two sizes of matrices. We have the 2x2 matrix and the 3x3 matrix. Okay, you don't have to have what we call square matrices. So these numbers can be different, and you can have like a 2x3 matrix or a 3x2 matrix. You can have bigger numbers than 2 and 3, have a 5x8 matrix, whatever. But for this section, we're going to just restrict to 2x2 and 3x3. Okay, these are probably the most common matrices we're going to see in this class. But again, if you've taken that linear algebra class, you've definitely seen weird sizes and stuff like that, and seen how to take it, how to deal with those and what you can do with those. So in the 2x2 case, there's 4 numbers, and we usually, when we're writing one in general, we'll write the numbers in here. We'll give them some labels. In this case, I'm saying A, and then we'll give them subscripts having to do with where they are in the matrix. So this is in the first row and the first column. So we call this 1, 1. This, if I put another thing here, this is also in the first row, so we put 1, and then it's in the second column, so we put 2. I know it looks like a 12, but you should read these as not like numbers. This is not 11 and 12. This is 1, 1, and this is 1, 2. Okay, you can put a comma there if it makes you feel a little better. The comma can get kind of hard to read. And so then here you can imagine this is now still in the first row, but now in the second column. So this is 2, 1, and this is A, 2, 2. Now, what always throws me is it's kind of arbitrary which one goes first. Like, why isn't this one 1, 2 and this one 2, 1, right? And so this is just like the convention that someone chose a long time ago, and now everyone does it. It doesn't have to do a lot with the math, but it's important that you do kind of get it in the correct order, just so that no one's confused when they see your work. No one's like, oh, why is this in a weird order? Okay, just because this is the way how everyone does it. So this 2, 1, it's always going to be in the row column. So it's also a similar thing when you say this. So for example, if I said 2 by 3, that would be 2 rows and 3 columns. Whereas 3 by 2 is 3 rows and 2 columns, which is different. So if you ever forget like what order to put these numbers in and like how that corresponds to its position here, it's always the row comes first and the column comes second. I always remember RC, and for some reason that helps me remember. I think isn't there like the soda RC cola? I think that helps me remember little mnemonics like that. This is one of those things that's not like deep mathematics. It's just like for some reason they always put it in the same order, and you have to kind of remember what order it is in order to kind of communicate effectively with others. Okay, so you can do a similar thing. We can fill all of these in. We could say A1, 1. So now we fill in all of this row. So A1, 2, A1, 3. Okay. So notice all of these start with 1 because they're all in the first row, and we always start with the row. A2, 1, A2, 2, and A2, 3. Now A3, 1, A3, 2, and A3, 3. Okay. So far matrices are just like some way of organizing a bunch of numbers in a way that's a little easier to read, right? Like if you just had a list of 4 numbers, that would look more unwieldy than like this 2 by 2 grid of numbers, right? It's a little more organized in this way. Same thing over here, there's 9 numbers, but when you put them in this grid, it's a little easier to manage. Okay, but algebraically, they actually do some interesting stuff. So later on Monday, I think we're going to discuss how to multiply matrices. We're not going to get to that today because just for time reasons. And today we want to focus on some slightly different stuff, but you are able to multiply matrices in certain conditions, which is kind of a nice feature. So you can actually do algebra with these matrices in some sense, and so we will discuss that. But today we want to talk about taking determinants. Now, determinants can only be taken for square matrices, and since today we're talking about 2 by 2 and 3 by 3 matrices, we're going to specifically talk about how to take these determinants here. So if we're taking the determinant of a 2 by 2 matrix, again, this might be a little bit of review for some of you, especially if you've taken a linear algebra class. Basically, what you're going to do is for a 2 by 2 matrix, you're going to do this main diagonal. So we always call this diagonal here going from top left to bottom right. We call that the main diagonal. And you're just going to multiply those together. So you're going to say A1, 1 times A2, 2. And then you're going to do the same thing on what we call the off diagonal, which is the other diagonal going from bottom left to top right. And you're going to multiply those. 2, 1, A1, 2. And then you're going to throw a minus sign in between. Okay. So here we have this. It's this minus this. And so it is important which order these go in because of this minus sign, right? So if you do it the other way, you're going to be off by a negative. And so that's important. Okay. So the 2 by 2 is not bad. In fact, with not much practice, you can get pretty good at looking at a 2 by 2 determinant and just computing a 2 by 2 matrix and computing the determinant in your head. But the 3 by 3 determinant is going to get kind of wacky, and we'll see that in just a second. Before that, I do want to make a note on the notation here. So notice up here, I had little brackets. Okay, and down here, I have these like giant absolute value signs. Okay, so the giant absolute value signs is the symbol for take the determinant of this matrix. So this as opposed to this means take the determinant. It's kind of a shame that it's such a subtle difference, like especially when they're big, you can kind of like lose track of these little, even in the typed version. I think maybe even especially in the typed version, sometimes that's kind of hard to see, and you don't notice right away whether it's the determinant or just they're just talking about the matrix. But just as a note, typically when we want to take the matrix or the determinant of something, we put these absolute values symbols around it. And so this is shorthand for this, the number you get when you could do this computation. Okay, cool. So just as like a little helpful visual, I like to say we take this and then we subtract this. Okay, so that's kind of what I'm picturing in my head. I'm going like this, and then I'm subtracting going like this. Might be mirrored for you, so maybe like this and like that or something like that. But yeah, so just these two arrows, I kind of visualize them happening here. Now over here, in the 3 by 3 case, things get even more tricky, right? Oh, I forgot to underline that. But yeah, so over here, we're going to, we have this big 3 by 3 matrix. And so what ends up happening is we take what you can picture happening is we're going to take it we're going to fix the first column, or sorry, the first row, and we're going to take it one column at a time. And what we're going to do is we're going to say ignore this column and ignore this row, and we're going to look at this determinant. Oh, come on. Okay, this determinant right here. Okay, so what do I mean there? We're going to say, okay, we're going to take this A11 and multiply it by the determinant of this smaller matrix. Sometimes it's called a minor here. A3, 3. Okay, so we deleted this row in this column, and then we just took this remaining 4 by 4 matrix and we take its determinant. Okay, that's the first step. That's the first term. Okay, and then we replace, we go back, and now we just keep doing this still with the first row. We still delete the first row. Okay, but now instead of deleting the first column, we delete the second column, and we take A22 or A12, right? Again, because that's what the column we deleted. And now we take these remaining 4 as a matrix and we take the determinant. So this one's harder to see because they're not next to each other, but we see A21, A21, A23, A31, A33. Okay, and now the weird thing is that this one gets a minus sign. Okay, I guess that's not super weird because there's a minus sign here. But then move this over here. We again forget these got deleted, and now we delete the first column, the first row, and the last column here, and we get plus A13 times this last these 4 here, the determinant of that. So A21, A22, A31, A32. The determinant of that. Running out of space there, but hopefully you can see that. Okay, so the sign here is alternating. So you do plus, minus, plus. Okay, and basically you're looking at the minors you get here, or the 2x2 matrices you get from these columns, and you just basically get that by first you delete this row or this column, and you get this 2x2. Then you delete the middle, and you get this, and then you delete this right one, and you get this 2x2 here. Okay. So it's a little hard to keep up with all of these without like the formula. So we're going to jump into some examples here in just a second. Okay. First, I want to make sure everyone gets this formula down before I move on. Okay, cool. Any questions before I move on to the examples? Maybe you have too many questions, and I should ask that after we do examples. Yeah, that's a good. Someone messaged me. That's a good point. So these still need to be computed, right? But I didn't write out exactly what they are here because basically you would just use this formula now. So you still need to compute all of these, I guess. Need to compute. In practice, when you actually go to do a problem, you're going to have to go and compute all three of these. These are still determinants that need to be computed. But in the formula, this formula would get super long and messy if I actually wrote this out, because I'd have to basically, each of these would be replaced by something that looks like this, right? So A11 times A22, A33 minus A32, A23, right? And then so on and so forth. So yeah, absolutely right. There's still more to be done, but the formula just kind of says, well, you already know how to do a 2x2, so I'm just going to leave it by that, like that. Okay, good question. Yeah, so once you compute these, you like, this is a multiplication happening here. So this gets multiplied by the number you compute here. This gets multiplied by the number you compute here, and this gets multiplied by the number you compute here, and then you just simplify with the plus and minus stuff. Cool. Yeah, we'll see some examples here in just a second, which I think will help clear some stuff up. Okay, cool. So here are some examples that I want us to compute. So we'll start with number 1 here. So we're going to compute the determinant of 2, 1, 3, 4. Okay. So again, these are 2x2s. The 2x2s shouldn't be too bad, right? So we have 2 times 4, which is, so 2 times 4 minus 3 times 1, right? Again, I'm just doing, in my head, I'm saying this diagonal minus that diagonal, okay? This is going to give us 8 minus 3, which is 5. So the determinant of this matrix is 5, right? So far, not bad, right? Like, that's pretty straightforward. Get this, take these two numbers, or take these 4 numbers and just kind of follow that, okay? Let's see with 2. 2, it's a very similar matrix, 3, 4, 2, 1. So notice what we did is we switched the rows here. So we flipped these 2 rows, okay? Let's see what that does to the determinant. Well, now the main diagonal, that gives us 3. The off diagonal gives us 8. And so now we get -5. So switching rows is going to give us, it's going to tack on a negative sign. So switching rows changes the sign of the determinant. Okay. So if I switch the rows of, so if you have to compute the matrix, the determinant of 2 matrices, but you notice that one of them is just the same as the other one, except that 2 of the rows are switched, then you know you could just compute the one and throw a negative on it for the other one. Or take off a negative if it was already negative, right? Cool. Cool. Okay, so now for the fun part, right? We have to compute this 3x3 matrix. Now, I think for space, I'm not going to have enough space here, so I'm going to make a new page here and just copy this. Scroll down here. Okay, so let's get to work on this. So the first step, right, is just going through, delete this row or delete the first row, right? We're going through the first row. Just a note, technically you could do it with any row, but we just, for the sake of simplicity, we always do the first row. Okay, so we delete the first row and then we go column by column deleting. So first we delete this first column and we throw -1 times the determinant of this little guy. So 1, 3, 4, -2. Then we subtract this 2 here and we delete this column and we get 0, 3, -2, -2. Okay, and then we add on this 1 times the determinant of, well, we delete this column here and we just get 0, 1, -2, 4. Okay. Cool. So that's the setup. I'm not done yet, but are there any questions so far? I'm feeling okay. So notice that like these numbers here are just these 3 numbers. That's all we're doing. And then these little 2x2s are just, okay, we deleted that matrix, delete that, it's the remaining matrix there, delete this, and it's this little matrix here. Cool. So far, so good? Okay. Cool. Next, we're gonna actually compute these little determinants. Okay, so we have -1 and then -2 minus 12, right? So all I'm doing is 1 times -2 is 2, minus 4 times 3 is 12. These sort of computations, I will warn, is like the type of computation where it's like super easy to lose track of your minus sign, right? And you lose a little minus sign here and it throws off the whole problem. And you're like, why is my answer different or something like that? Or I do it in front of you all and you all notice and I don't for like 5 minutes. Okay, so we do the determinant of this. So the main diagonal gives us 0 minus -6. So that's exactly what I'm talking about. So -2 times 3 is -6, but we're subtracting that. So it's just a 6 here. Okay, plus 1 times, again, we have 0 on the main diagonal, again, minus a -2. So plus 2. Okay, so let's simplify this. We get minus -14 minus 12 plus 2. Let's see. Okay, this is 14 minus 12 plus 2, so we get a 4 here. Cool. Did I make any mistakes? This is definitely the type of problem where I would make a mistake, so let's double check everything. No, it looks good. Isn't 6 negative? This one here. So we have the main diagonal would be 0. The off diagonal would be, right, so it's 0 minus -6. Yeah, so this is what I'm talking about, right? Because it would be 0 times -2 minus -6. Okay. Yeah. Why isn't the last part plus 1? Here, this is plus 1 times 2, right? So, because right here we have, again, 0 minus -2. So 1 times this determinant, which is a positive 2. Yeah, and the signs are alternating. So we have -1, and then -2, and then +1. So I guess plus -1, -2, plus +1. Yeah, good questions. If I had all the time in the world, I would do like 20 of these problems. but I don't have all the time in the world to just do it in front of you all. And also, I think it's more beneficial for you to do some yourself. So I think like the first problem on homework 1.3 is just like compute a bunch of determinants. So I definitely suggest after this class, when you get a chance, just go through and do at least that first problem, but definitely also try to keep up with the rest of the homework. But at the very least, go through, do that first problem, get your practice in now. It's best to like, this is the sort of computations that it's like, it's best to get the practice in now. There are calculators online that like compute determinants for you. So it's like, at the end of the day, it's, you know, most in the future, most of the time, you're probably not going to be computing your own determinants, but it's important conceptually and, you know, for the sake of like understanding, to understand how the formula of for computing the determinant works, because eventually you're gonna need to know how the formula works in order to actually compute it, right? Okay, cool. This is the sort of problem where it's easy to make a problem up, right? Because you can just throw 9 random numbers here, and you can just compute the determinant and see what happens. The arithmetic might not always be nice, but you can do it. Okay, and it's the type of thing that, like I said, is easy to check your work because it's easy to teach a computer how to do it, and people have already done that. So you could just throw it in a calculator somewhere. Okay, cool. Any other questions on this before we move on? So basically, this is how you compute determinants. But now, what are they good for, right? So let's talk a little bit about what they're good for. So first, we're going to start with 2x2 determinants. Basically, for the first 2 lectures, I was saying a lot of like, I'm doing this in 3 dimensions, but it works also in 2. And then, you know, I was saying a lot of that. This is where things start to get pretty specific to each dimension, okay? So specifically in dimension 2, if we have 2x2 vectors, then they're going to give you a parallelogram, right? Let's see that in a way that's maybe a little more concrete. So if I have a base point somewhere, and then I give you a vector A, and then another vector B, you get a parallelogram basically by making a copy of A over here. So I'll do my best to make a copy of A, and then a copy of B up here, and then they meet because it's basically B plus A is the same as A plus B, right? And so you get this parallelogram, right? Which maybe you've seen before, right? The diagonals of this parallelogram are plus and minus, right? If you remember from our arithmetic stuff. But basically, you get this parallelogram. And the question is, oh, okay, how do we compute the area of this parallelogram? Well, I mean, you have like old school geometry ways, but in this case, it might be kind of hard to get the numbers you need for that, right? I mean, I guess the length of the base is not too hard, but then the height of this might be a little more difficult. So it's easier to use determinants in this case. So basically, the area of this, let me move this, the area of this parallelogram is going to be the determinant of, I should say maybe the absolute value of oh gosh, that's ugly. The absolute value of the determinant of A2, B1, B2. Okay, so basically we take these vectors and we put them into a into a matrix like this, just stack them on top of each other, take the determinant, and you get the area of this thing. Now, technically, determinants can be negative, as we saw, so you throw an extra absolute value of this on this, okay? If you're careful about the order, so I think if you, I did it wrong here, I should have gone in the other way, but if you go, make sure that you're always putting, if you're going counterclockwise, put the one on the right first, right? So if you're going counterclockwise, B should go first. So B should go on top. If I had done this B1, B2, then I wouldn't have to take an absolute value. That's just a little trick. Or you could just put them in whatever order you want and just remember to take the absolute. Just remember that area should be positive. Okay. Cool. Yeah, and there's something to be said, and we'll talk a little bit more about this when we get to cross products and stuff, which I'll talk about in a bit, about the order in which you put these determines is determined by the geometry here. I guess the sign you get is determined by the geometry of this. Okay. Cool. So let's see this in action. And I'm not just going to give you two vectors and have you determine the parallelogram. I want you to actually use it, and I'm going to actually do it in a creative way. Also, this is going to be helpful because there's a problem like this on the homework, and so it would be nice to see it. Okay, so I'm going to go ahead and just draw a picture of the triangle that we're trying to find the area of to start, and then just kind of see if we can use that to figure out how we can use this formula, which is about parallelograms, and you have two vectors and you get an area of a parallelogram. Now we have 3 points and we want the area of a triangle. So it's like, seems like a different problem, but we're going to see if we can use that to figure out this. So start by drawing a picture. So then you can kind of get an idea of what's going on. So the 3 points we have, which I'll do in another color. So we have 0, 1. We have 2, 2. We have -1, 3. So the picture we have is this triangle here. Oh. Okay. Cool. So this is the triangle here that we want to compute. Okay. And now there's a few ways to go about this problem, but basically what you want to do, of course, you can try to figure it out using your old school geometry, which in this case actually looks like it might actually work out pretty easily, but in general, that might not be so easy. So what you want to do is think of these 3 points as the endpoint of some vectors, but then you're noticing like, oh, well, our formula up here in the last slide, you need 2 vectors, but we have 3. But also the tip of this parallelogram, because of the way vectors work, is sitting at the origin, right? So typically we think of this as being the origin. Okay. And so over here, what we need to do is move one of the edges here of this, or one of, not the edges, one of the vertices here, one of the points, the tips, to the origin here. So we can just shift all of this down by this point here, this point closest. But again, we can also do it with any one of these points. So what we just need to do is pick one of these points and subtract it from here. So basically, we are going to convert this picture to a different picture and then use that other formula. So we get a coordinate grid. Okay. And all we're going to do is we're just going to move everything down by 1. In this case, we could have picked any one of these points to subtract by. But basically now, these 2 sides of the triangle, right, are actually vectors here. So we can actually think of them as vectors connecting to these 2 points. And let's take for a second to figure out what these vectors actually are. So originally this vector would have been, right, this vector here would have been 0, 1. This vector here is 2, 2. And this vector here is -1, 3. But by moving everything down, we've now subtracted this vector from everything, right? We've subtracted 0, 1 from everything. So this vector here is 2, 1, right? We subtracted 0 from the x coordinate and 1 from the y coordinate. And over here we get -1, 2, because again, we're subtracting 0 from the x coordinate, 1 from the y coordinate. Okay. Now we're thinking, okay, great. We have 2 vectors, but they're the sides of a triangle, not of a parallelogram like we want over here. But if you know just a little bit about geometry, right, then basically this triangle is half of a parallelogram that you get from doing something like this, right? So you do this parallel. In this case, it actually looks like it's a square, right? But in general, it might not always be a square. It might be just a weird parallelogram. And if we had chosen a different point, then we could have like moved this point over here. Then we wouldn't necessarily end up with a square like this. But basically, this is going to be the area of the triangle. So the area, area of the triangle is going to equal half of the area of the parallelogram. Okay, so neat little trick. And then so the area that we're looking for, which is the area of the triangle, is going to be 1/2 times the determinant of the matrix 2, 1, -1, 2. Okay. So I'm using these vectors here. Okay. Now I take this determinant, I get 1/2 times 4 minus -1. So I get 5/2. Okay. So someone asked, does it matter which point we put on top? Like maybe your first instinct was to say, okay, -1, 2, 2, 1. Like we saw when we were computing determinants, all that does is it throws in an extra negative sign. So what that would have done, if you had put them in the opposite order, you would have gotten a -5 here, which then you can just say, okay, well, we're computing an area, so then we drop the negative sign, right? So all that's going to change if you change the order here, which one goes on top, is the negative sign. Now, what I was trying to explain, and I don't think I did a great job of explaining, is the way you guarantee that you get a positive number is you always move counterclockwise, right? So you start at the as far right as you can and go move counterclockwise. Okay. Yeah, you imagine, like I would like to imagine I'm standing on this point looking into this area. The vector on your right goes on top. The vector on your left goes on the bottom. Okay. Cool. Cool. Other questions? Yeah, so I think a question like this comes up on the homework. So hopefully you'll get a chance to take a look at that soon. Okay, get your practice in. And sometimes they're even really nice, and one of these points is already the origin, in which case that's even less work. Okay. Cool. Let's move on. So we're going to do something similar with 3x3 matrices. But you might be thinking, okay, well, in 3 dimensions, there's not parallelograms, but there's these objects called, use a new vocab word, parallel pipets, or parallel pipoids. Sorry. And it's basically, you can imagine, right? So to get a parallelogram, you take like a rectangle, and then you just kind of do this. You skew it, so that it's kind of like a weird angle. You do the same thing with a rectangular prism in 3 dimensions. You kind of like skew it so that any 2 opposite sides are going to be parallel to each other, but it's all kind of at a weird angle, and that's what a parallel pipet is. And so I'm going to draw the picture over here. So basically, you should picture this living in 3D, and basically, if A and B are on some plane, you just do the regular parallelogram here. Okay, but then you also have to go back into this 3rd dimension and connect all of this stuff. And my drawing is not the best, but hopefully it gives you the right picture. So it looks kind of like a cube or rectangular prism, but it's all kind of askew here. So it's kind of like, whoop. There are better pictures, of course, in the textbook or online if you look up a parallel pipoid. Sorry, I keep messing that word up. There's better pictures online, and yeah, so that's the sort of shape we're trying to get, and you can compute its determinant. Sorry, you can compute the volume of this. So there's a little boo-boo there. That should say volume, right? Because we're talking about a three-dimensional shape. So it doesn't have area, it has volume. And the volume is given by this, this vector here, the determinant here. So the volume is going to be by the determinant of A1, A2, A3. So just like before we stacked the two vectors on top of each other, now we're going to stack the three vectors on top of each other. And this one, it's a little harder to see which one should go on top. Well, it's actually quite a bit harder. And I think this one is definitely one of those where you should just put them in any order and then just make sure it's positive. Take the absolute value. Yeah. There are ways of like putting them in a certain order to make sure that you get something positive, but it's a little harder to see based on the picture. So I think what I did there was actually not quite right. This order would actually probably get you something negative, I believe, but we'll actually learn a little bit more about this in a second. But again, with something like this, I would probably like not even bother taking the time to figure it out and just put it in some order and just take the absolute value, which in other words means make sure it's positive. Cool. Any questions about this? Cool. So this is like a useful thing you can do with determinants. You can just kind of take areas and volumes of these shapes. Okay. Let's see what's next. Next is going to be the cross product. So yesterday we learned about the inner product, which was we also called the dot product because there's a little dot between them. Today we're going to learn about something called the cross product. So if you remember, one thing I talked about when we talked about the inner product or the dot product is that the dot product takes a vector times a vector and gives you a number. Here we're finally going to do a vector times a vector gives us a vector. With one caveat, right? It's a pretty big caveat. The inner product or the dot product works in any dimension. The cross product, and I will highlight this, only works in 3 dimensions. Okay, so the cross product is something that's unique to 3 dimensions. Nothing like it exists in 2 dimensions or higher, or 2 dimensions or in higher dimensions like 4 dimensions, whatever. Which we haven't really talked about higher dimensions. So, but just so you know, once we get there, this is only going to work in 3 dimensions because let's see the definition here. Basically, you have 2 vectors, and you want to get another vector out of those 2 vectors. The way we do that is we set up this matrix where we have ijk. Remember what ijk are? That's just what we call the standard basis vectors, right? Standard basis vectors, meaning they were kind of these 3 vectors ijk, which gave you that kind of generated the xyz axes, right? And then you have the coordinates for each of the vectors here. Okay. And you get this determinant here. Okay. Now, an important thing to notice here is that when we say it's defined symbolically, basically in a matrix, the entries should all be numbers, but notice that we have vectors here. Like that's a vector, right? These 3 are vectors. So technically, this is not a proper matrix. So you're not actually taking a determinant. But intuitively, this is what you're doing. You're just setting it up this way and taking the determinant. For the sake of computations, this is how you're going to think about how to take a cross product. Take the determinant here of this matrix here. Okay. Now, importantly, you're going to want to have some intuition as to what the cross product actually is. Okay. And what the cross product is giving you is actually what's Basically, you're going to get, if you have the two vectors here, okay. Again, we should be living in 3 dimensions. So let me try my best to make that happen. So if this is U and this is V, what this is doing is it's giving you a vector which is orthogonal to both of these vectors. Okay, let's give something like that. Or oops. So this vector here is V cross U. Okay. Okay. Now, a couple of things I want to point out here. First of all, this vector is orthogonal to both of these vectors. We're going to learn on the next slide. We're going to learn a new vocab word for what else we can, for something else we can call this vector. But this vector is orthogonal to both of these, means it forms 90-degree angles with both of these vectors. Okay, but notice in this case it's pointing up, right? There's another vector that's also orthogonal to both of these vectors. Of course, I could scale this up and down, but we'll talk a little bit about what the magnitude of this is. Actually, I might want to say that now. But basically, there's another vector in the opposite direction, which also looks like it's at a right angle to both of these, right? And it is at a right angle to both of these. And you might say, okay, well, why isn't this V cross U? Well, it turns out that this is U cross V. If you notice here, by switching what U and V do, you're switching these rows. And what happens in the determinant when we switch rows? You just get a negative sign. So by taking this and switching the roles of U and V, in other words, switching U from V cross U to U cross V, it flips the whole vector in the exact opposite direction. So just throws a negative sign. Bloop, 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 right? And you might be remembering, okay, how am I supposed to remember which one is which? Now, if you've taken a physics class before, maybe you're like, you have the answer and you're just dying to say it out loud. But the way you remember is something called the right-hand rule. Right-hand rule. Okay, and this is not the easiest thing to explain, but what you do is you use your right hand to kind of signify or to kind of help explain which way then the norm, or sorry, the cross product needs to go. So since we're going V cross U, right? Then what we're doing is we're going to look at V and U in space. And we're going to start with V, and our fingers here are going to represent V, and they're going to sweep till they get to U. Okay. So in this case, that means we're going with you have to use your right hand with this. It doesn't work with your left hand. You go from V, and then it sweeps counterclockwise to get to U, right? Counterclockwise to get to U. And now my thumb is going to be pointing in the direction of V cross U. Okay. So if we're looking down at V and U, going counterclockwise this way, boom, it's harder to draw on paper. It's easier to do in like real 3-dimensional space, right? So if we go counterclockwise from V to U, then the upward position in that case is V cross U, right? But if we were looking at this from the bottom, right, then it would be going from U to V would be going counterclockwise. And so the cross product would be pointed down. So going from U to V, in order for my fingers to sweep from U to V, right? Then now my thumb has to be pointed down, right? And that's why the normal vector goes in the other way. Okay. So like play with this a little bit, like inevitably it's more fun in person, because in person you look out into the lecture hall and everyone is like doing this. And, but just give it a try yourself, kind of try to make sense of that. It's hard to communicate on paper how to do that because, right, paper's 2-dimensional. It's hard enough to draw things and let a note explain slightly more abstract concepts. But here, just try to do it in 3-dimensional space. If you have these two vectors, you can also do something like this, right, where you have kind of these two vectors these two are the vectors, and then this is the third vector shooting up. But I think curling the fingers also is what usually helps me. Like this, these fingers are like sweeping in the counterclockwise direction. And so going from V to U, like if you're trying to grab V and U as vectors, you want to start with V, because V, when you're doing V cross U, you start with V and then you sweep to U, and then now your thumb is pointing in the V cross U direction. Okay, and then U cross V, if you start with U, you have to go this way. Okay, cool. Does that makes any questions on that? It's a little weird, the right hand rule. Okay. And now I also mentioned that this, right, I could scale this and still get an orthogonal vector. But the length of this is important because basically, even in three-dimensional space, you still get like a parallelogram, except that the parallelogram is now floating in three-dimensional space. And so the magnitude of V cross U is the area of the parallelogram. Parallelogram. Okay, sounds kind of a weird one to see. But yeah, basically you get the area of this parallelogram here. Okay. Which is weird to think of the, like when you think, oh, well, we already did an area of a parallelogram, but this was a parallelogram in two-dimensional space. Now we have a parallelogram floating in three-dimensional space. Okay. Yeah, it's not a parallelepiped because there's only two vectors. So just take this parallelogram floating in three-dimensional space. Okay. Any questions on this? The cross product is definitely weirder than the inner product, but I think geometrically it's more meaningful, right? The dot product was gave you the angles. The cross product is giving you this extra vector, okay? And it also gives you, and like along the way, it gives you the area of the parallelogram. So it's doing like two things even. Okay, cool. Someone's asking, how do we know if it's 3 or 2 dimensions? Sometimes it'll say things like it's R3, but the key here is how many coordinates you have. If they give you 2 vectors and the vectors have 1, 2, 3 coordinates, then it's 3-dimensional. If it only had 2 coordinates, then it's 2-dimensional. Yeah, so the number, the dimension is determined. It's basically just saying how many numbers do you need in order to tell me what direction the vector is pointing in. In this case, you need 1, 2, 3 numbers. Cool. Yeah, and yeah, so that kind of also leads to why the cross product only works in 3 dimensions, right? Because notice we have 3 columns, 1 for each dimension, and then if we fill that in with the ijk, then that leaves us 2 rows left. Right? If it was any more, if this was a 4x4 matrix, we'd have 3 rows left. That's not enough to fill in with just 2 vectors. And back in 2 dimensions, there would only leave 1 row, so we can't. There's no cross product in those cases. Okay, cool. How am I doing on time? Not great. Let me quickly define this this word here called the normal vector. So this is where this word kind of comes up in different ways. So we had the norm, which was the same as the length or the magnitude of a vector. We had normalizing a vector, which was taking a vector and turning it into a unit vector. Okay, now we have a normal vector, which is, again, not related to the other two, which I understand is confusing. So it's orthogonal to every vector on the plane. So basically, if this here is a plane, then this here is your normal vector. It's kind of perpendicular to the plane. In 3 dimensions, basically, if you imagine you have like a piece of paper in 3-dimensional space, there's only one direction that's perpendicular with this piece of paper, right? You imagine you have some surface in 3 dimensions. There's only one direction that's perfectly perpendicular. And so that's what we call a normal vector. Now, the normal vector might be, you might have a really long normal vector like I put here, like I drew here, like this pen is really long, or maybe you have something a little shorter. I don't have any shorter pencils or anything, but you can imagine it can be different long. So there are different lengths. So this is kind of what we have here. So an example of this is the cross product. So that's what the cross product is kind of doing. If you have two vectors that live on a certain plane, the cross product is giving you the normal vector to that plane. Okay, so this is kind of a different vocabulary for talking about this sort of, over here I said it's orthogonal to both vectors. Oh, maybe I didn't write that anywhere, but right, so maybe I'll write that here, that's worth saying. So V cross U is a normal vector to the plane spanned by V and U. So basically these two vectors, right? If you have two vectors, then that gives you some plane, right? But anytime you have two vectors, that's going to give you some plane. If you have two three-dimensional vectors, then it gives you a plane in R3, and the cross product of those vectors is going to give you the normal vector. Okay, cool. So we're just about out of time. Any last minute questions before we move on, or before we call it a day, I should say? Cool. If there are no other questions, we can call it a day there. Thank you all for joining.